How's it going, everyone? Today we're going over ATP pathways. So let's start with the first one is glycolysis. So that's breakdown of glucose in order to form pyruvate and of course ATP. It's a 10 process step and the end goal is to create pyruvate in order to go either anaerobic or aerobic direction. So the first part we think of as the investment phase. So in this phase, we have to sacrifice 2 ATPs in order to attempt to create more. So we think of it as investment phase because just like money, when you spend money, you invest in something and then you get that return and more. So right here you already see 1 ATP in step 1 loss and then you see 1 ATP in step 3 lost. So total minus 2 ATPs. So the next part we have is PFK, which is a coenzyme, stands for phosphofructose kinase. And it's important because in this situation, if phosphofructose kinase is not in a right state, then this process ends there. It will not continue. So things that make PFK not want to continue is the temperature, so increase heat, or if it's too acidic in the muscle. So we go to the next process and we see that we get NADH. So that's going to be important later. And one thing to notice is that after step 5, it splits into 2. So at this point, everything is by 2. So what happens one side happens the other side too. So 2 NADHs. And then we see ATP finally be created right here at step 7. ADP converts to ATP. There's some energy. There's 2. You see 2 more at step 10. So in total, you have 4 created, 2 lost. So you have a net total of 2. Then we get to the end point, which is pyruvate. Again, that is where we decide whether or not we want to go anaerobic or aerobic route. So let's say it's anaerobic. Pyruvate gets converted to lactate. And that just ends there. Well, actually, NAD has to be recycled back. So NAD loses that hydrogen and lactate takes it. That forms lactic acid. And NAD is brought back and recycled to be used again. So that ends anaerobic. So let's talk aerobic glycolysis. So pyruvate, there's 2 pyruvates. So the next part goes into the citric acid cycle. As you can see, the pyruvate here, like I said, there's 2 pyruvates. So everything you see here is doubled. This is just one side of it. Again, here you see an NADH. And then you get to this coenzyme here, which is called coenzyme A. That's also important because in order to start the citric acid cycle, you need acetyl-CoA in order to actually get this thing going. So you don't really need the pyruvate. You could actually skip right to, if you have acetyl-CoA, you could just start this citric acid cycle automatically. So when we look at the citric acid cycle, we see familiar things, NAD here, 1, 2, and 3. We also get introduced to FADH, also gets converted to ATP later. And here we are, we have a ATP right here. And the way this is converted is GDP, it collects a phosphate, and then ADP collects a phosphate from GTP, and ATP is created. So let's add up everything we have so far, right? So through glycolysis, we had 2 ATPs, 4 produced, 2 were sacrificed. We had 188 or 2 NADHs. In pyruvate, we have 1 NADH here. And remember, there's 2 pyruvates, so multiply that by 2. So the citric acid cycle is 1 here, multiplied by 2. There's 2. And then 1, 2, 3 NADHs. That's 6 when you multiply it. And then we have 2 FADHs. So why is this important? It's important because these here, they actually produce ATP later on down the line. So let's go over that right now. So looking at the electron transport chain, When you look at it, you see all these hydrogens, you see 5 complexes. So let's see, starting off with NADH. NADH gets broken down into NAD, and then electrons are released into complex 1. At that point, this allows 4 hydrogens to come in from the matrix into the inner membrane space. And to continue that, these electrons want to go down the chain. This Q right here, it stands for ubiquinome, and that is a coenzyme that carries this electron all the way down into the 3rd complex. Again, electrons in there allows 4 hydrogens to pass through, and then electrons go down the chain to C, which is cytochrome C, into complex 4. And at this point, it's different than 1 and 3. Complex 4 actually only lets 2 hydrogens in. Now let's look at FADH. So FADH gets broken down, electrons go into complex 2. Now complex 2 is shorter than the other ones, if you can see that. So it doesn't let any hydrogen in. Instead, it just follows down into the Q, into the ubiquinome, and then follows down to 3, and into C, and then 4, right? So NADH has 4 plus 4 plus 2, so it has 10 hydrogens. And FADH, it produces 4 plus 2, that's 6 hydrogens. Why is that important? Over here in complex 5, we have what's called a ATP ACE. And what that does is it allows hydrogen to come from the inner membrane space and go in here and produce ATP. It allows 4 hydrogens to come in, and that produces ATP. So if we look at that, we have, remember, 10 hydrogens created by NADH. So 10, and then 4 is converted into ATP. So if we take 10, divide that by 4, we get 2.5 ATP. We do the same for FADH. So we have 6, 4 plus 2, that's 6, divided by 4, H plus. So FADH converts into 1.5 ATP. So here we are. Let's add everything up. So from everything we have, we tallied up all the NADH, all the FAH. So we have 10 NADH from the combination of glycolysis, pyruvate, and citric acid cycle, and we have 2 FADHs. So first of all, we have the 4 ATP from glycolysis. Those are direct transfers. And citric acid cycle, that's 4. And we have 10 NADHs. Multiply that by 2.5 ATP because NADH produce 2.5 ATP. We get 25. 2 FADHs. Multiply that by 1.5. And that's 3. Add that together, we have 32 ATP produced in aerobic glycolysis. The last ATP pathway we're going to look at is beta oxidation. So we're going to break down this palmitic acid, which is C16, H32O2. So you look at the structure here, and each of these represents a carbon. So 1, 2, that's 3, 4, all the way down to 16 carbons. So what we want to do first is break those down. So we're going to pair them. And in order to break them down, we sacrifice 2 ATPs in order to do so. So that's one cut. In order to make cuts, we sacrifice 2 ATPs. So I make a cut here. I'm going to make a cut here. Cut here. Eventually, all the way down, I get pairs. So just like that. So I make 7 cuts. And those 7 cuts end up becoming 7 NADHs and 7 FADHs. So now what I want to do is just pair these guys up. So these, after I make the cuts, these things break off and they become acetyl-CoA. So there's 1, there's 2, 3, 4, 5, 6, 7, 8. So those are 8 acetyl-CoAs. So again, in total we have 7 cuts, so 7 NADHs, 7 FADHs, and 8 acetylcholines. And remember these numbers, 2.5 for the NADH, 1.5 for the FADH, And then if we add up the ATPs in the citric acid cycle, which is the NADHs, the FADH, and then the 1 ATP, we actually get 10 ATP. So 8 acetylcholines times 10, which is 80. You add those up, you get 108. But then don't forget, we had to sacrifice 2 ATPs here. So you subtract that from your grand total and you get 106 ATPs. So that's 106 ATPs when you break down palmitic acid. So after learning all this, you might be wondering, what does this all mean? How does it relate? How can I utilize this? Well, let's just take glycolysis, anaerobic versus aerobic. When you look at anaerobic, it's a 10-step process. Yeah, it only produces 2 ATPs, but that's quick. It's very fast. So if you're trying to produce a 1 rep max, where you need all the energy you can in just a couple seconds, then yeah, you're going to want to utilize the pathway that gets you the most ATP the quickest. And that would definitely be the anaerobic glycolysis. In aerobic glycolysis, it's a 21-step process, almost doubled, more than doubled anaerobic, but it produces 32 ATPs. That's a huge difference. That's because your body knows that it has the time to actually produce all this energy for you to run your mile or run an hour. It helps you keep on going. And when you think of beta oxidation, you know how carbs are broken down now. You know how to utilize that to the best of your advantage. If you're going to work out, you can eat certain foods, you can eat certain or take certain supplements that will help you pretty much get the best workout you can. I hope that helped you understand ATP pathways a little bit better. Thank you.